Hi everyone, welcome to Chapter 2, Section 3. Today we are learning two more rules, so now that we have like the basic derivative rules down, we're going to get slightly more complicated with what we take derivatives of. So we're going to have two rules today, the product rule and the quotient rule. And so these rules are for when we have two things that are like being multiplied together or two things that are being divided by each other, and how to find the derivatives of those things. So to find the derivative of two things being multiplied together. So the rule itself, it's not the greatest way to explain it, but we'll do examples so you can kind of see. But if we have two things being multiplied together, find the derivative of the first thing, multiply it with the other. Then find the derivative of the second thing, multiply it with the original first. Okay. I know what the words that I said right there weren't the greatest explanation. So here we go with an example. So I have x squared times 2x squared minus 3x. So clearly I have two different things being multiplied together. I have the x squared and I have the 2x squared minus 3x. So if you want to think about that as like the x squared is the f of x and the 2x squared minus 3x is the g of x. So those are two things being multiplied. So the first thing we want to do, and this is how I generally set it up each time, we're going to find the derivative of each thing individually. So x squared, the derivative would be 2x. So that would be my f prime. And the derivative of the second part, the 2x squared minus 3x, if I use the power rule, then the 2x squared, the derivative would be 4x, because I would multiply the exponent with the front number, and then drop the exponent by 1, minus 3 for the minus 3x. Okay, so there's my derivatives. So I kind of think of this as cross-multiplying. So I'm going to take the original here, so the 2x squared minus 3x, and that'll get multiplied with the 2x. And then I'm going to take the x squared here and multiply that with the derivative, 4x minus 3. And then they get added together. And that's the product rule. So to me, I'm like, I make the cross because, you know, when you multiply, it's like x. That's how I remember it. So it doesn't matter which order because we're adding. So we can do either thing first. So I'll go x squared times 4x minus 3 plus the 2x times 2x squared minus 3x. So just following along the x. And then simplifying that out, I end up with 4x cubed minus 3x squared plus 4x cubed minus 6x squared. So simplifying everything out, combining like terms and stuff, I end up with 8x cubed minus 9x squared. So basically each time we use the product rule, we just have to recognize, oh, there's two things being multiplied. This is when I would need the product rule. If you had three things being multiplied, then we can't do it this way. It only works if you have two things being multiplied in your original equation. Let's do another example. So let's say I had the equation f of x equals x squared times e to the x power. Okay, so here, again, clearly I have two things being multiplied together. I have the x squared and the e to the x. So we're going to find the derivative of each thing. X squared, the derivative would just be 2x using the power rule. E to the x is that special one that the derivative is just itself, so it'll just be e to the x. And then we're going to do our cross multiplying again. So this way and this way. So the derivative of f of x, otherwise known as f prime, we have x squared times e to the x plus 2x times e to the x. And then there's no like terms to combine, so that's it. Okay, so let's get a little bit more complicated now. We're going to throw in some trig in there. So my equation that I'm going to try to find the derivative of is 4x squared times sine x minus 7 times cosine x. So because I have a longer equation here, we can always split this up. Remember the sum and difference rules. We can just do them separately. So I'm going to start by focusing on the 4x squared times sine x. So 4x squared times sine x, those are my two separate things that are being multiplied, so I need the product rule for that one. So 4x squared, the derivative would be 8x using the power rule. Sine x, the derivative is cosine x. So cross multiplying those together, I end up with 8x sine x plus 4x squared cosine x. And again, you could have done it the other way where you did 4x squared times cosine x first plus 8x sine x. Okay, now let's take care of the second part. So in the second part where the minus 7 cosine x, technically I have two things being multiplied. I have the 7 and the cosine x, but the 7 doesn't have an x in it, so that's just a constant. So you can do the product rule with this. It would just be like extra work. But if you recognize that this is just a constant, then we don't actually need to use the product rule because it's just a constant being multiplied to cosine x. So really, the derivative of cosine x would just be negative sine x because of that special rule. But then, so I have the minus sign, and then the constant stays there according to the constant multiplier rule. And then we multiplied with the derivative of cosine x, which is negative sine x. So simplifying this out a little bit, we're just going to end up with plus 4x squared cosine x, and then it'll end up being a positive 7 sine x. And that's our derivative. Nothing else to combine together because we don't have any like terms. So that's really it for the product rule. Quotient rule is a little bit easier to recognize when you see the problem because it's going to be in fraction form because you're dividing. So the quotient rule is a little bit more complicated looking, but your original equation is going to be something being divided by each other, so easy to recognize. But then the rule itself, there's a lot to it. I have a cool rhyme, well, I think it's a cool rhyme, to help you remember this, and I'll write it out for you. So if you read it as low d high minus high d low all over low low. So when I use this rhyme, let me use an example. That way we can kind of see how this works. Let's say, for example, I had the original equation of 5x minus 2 over x squared plus 1. Okay, so clearly I have two things being divided, so I would need to use the quotient rule because I got that fraction in there. So the first thing I'm going to do is take the derivative of both the top and the bottom. So 5x minus 2, the derivative would just be 5. The minus 2 part, it's a constant, so the derivative would be 0. On the bottom, x squared, the derivative is 2x. The plus 1, the derivative would be 0. Okay, so using the quotient rule, we are taking whatever's on the low, so on the bottom of the fraction would be x squared plus 1. D high would be the derivative of the top, which is 5. Minus high d low. So high is the 5x minus 2. D low is the derivative of the lower, which is 2x, all over low low. So whatever's on the bottom, we're multiplying it twice, so you're squaring it. Okay, so this would help us find the derivative of f of x. And then from here, we just need to simplify this out, so I'm going to multiply and distribute, so that 5 to the top, so 5x squared plus 5 minus, and then distributing out the 2x to everything. I get 10x squared minus 4x, but then I would have to distribute that negative to everything. So after distributing and combining like terms, I end up with negative 5x squared plus 4x plus 5 on top. On the bottom, even though we're like saying we're squaring it, we don't need to FOIL it out. We're just going to save ourselves some time. Leaving it in that factored form is perfectly fine. Let's do another example. So this time I've got 3x plus 1 over 2x squared minus 5x. So again, clearly in need of the quotient rule because I've got things being divided. So I'm going to find the derivative of the top, which is 3. And then the derivative of the bottom should be 4x minus 5. Okay, so doing our quotient rule, low d high. So low is the 2x squared minus 5x. D high is 3 minus high d low. High d low would be the derivative of the bottom, all divided by low low. So lower is the 2x squared minus 5x, and that just gets squared. Okay. So again, we're just simplifying by distributing the top and then combining like terms. So distributing that 3 will give me 6x squared minus 15x. Then I have a minus, and then the 3x plus 1 times 4x minus 5, I need to FOIL out. So, and I generally like to keep things that I'm subtracting in parentheses first. That way I remember at the end to distribute my negative. So that's what I get from FOILing. And then distribute my negative on top. Oh, I could have combined like terms too, but we'll take care of that. Okay, so on top, combining all my like terms together, I'm going to end up with negative 6x squared minus 4x plus 5 over 2x squared minus 5x squared. So there's my derivative. Okay, for this next example, let's add on a step to it. So rather than just finding the derivative, now I want to find the equation of the tangent line. So remember, that means we have to use our x value to plug in our derivative so that we can find the slope, and then use the point slope form to find the equation at the end. So same process, it's just we're making the derivative part more complicated. So for this one, we especially have a more complicated because our equation is 2 plus 1 over x minus 1. Ugh, ugly. We got fractions on top of fractions. So let's actually rewrite this so it looks nicer. Because if I have fractions on top of fractions, technically I would need to do the quotient rule twice, and that's, ugh, no. So if I rewrite this, instead of the 1 over x, I can rewrite this as a negative exponent, because remember, negative exponents turn things into fractions. So if I rewrite this as 2 plus x to the negative 1 power over the x minus 1, then on top, I don't have like more fractions to deal with. So using our quotient rule, on top the derivative, so for the 2, it's just a constant, so the derivative is 0. For the x to the negative first power, I'm going to have to use the power rule. So bring the negative, to bring the exponent down to the front, x, and then drop the exponent by 1 to get negative 2. If I were to rewrite this, I would have negative 1 over x squared. On the bottom, the derivative of x is just 1, minus 1 is just a constant, so the derivative is just 1. That part's nice. Okay, so let's find our derivative using the quotient rule. So we have low d high minus high d low, all over low low. Okay, multiplying stuff out. I'm actually also going to change that x to the negative first power back to a fraction because it'll help me multiply things out better. So in this first part, I've got the x minus 1 times negative 1 over x squared. Multiplying that out with x, I'm going to end up with negative 1 over x plus 1 over x squared. And then minus, multiplying this stuff out, I'm going to have to FOIL this, not the prettiest. So 2x minus 2 plus 1 minus 1 over x. Ugh. Okay, let's try to simplify this. Ooh, I think stuff cancels out. This is nice. So let me distribute my negative first. So then I end up with things canceling, my favorite. Okay, I think that's it. But still. So I have the 1 over x squared minus 2x plus 1 over x minus 1 squared. Okay, so at this point in time, I know I have complex fractions and I should simplify more. However, because this isn't my final answer is going to be the equation of the tangent line. So I'm just using the derivative to find the slope. So if I can, instead of simplifying more, just use this to plug in my x value to find the slope. Okay, so the x value they told me to use was 2 because the point that they want to be in this line is 2 comma 5 over 2. So we're plugging in x equals 2 to find the slope. So 1 over 2 squared minus 2 times 2 plus 1 over 2 minus 1 squared. So 1/4 minus 4 plus 1 over 2 minus 1 is 1, 1 squared is 1. Okay, so on top, I'm going to end up with a fraction. 1/4 minus 3 is negative 2 3/4. Negative 11 over 4. That's going to be my slope. Okay. So once I have the slope, then I need to use the point slope form to write the equation of the line. So that's that. Y minus y1 equals m times x minus x1. And we know m equals negative 11 over 4. We know my x1, y1 is equal to the 2, 5 over 2 that they gave us originally. So plugging everything in, I'm going to have y minus 5 over 2 equals negative 11 over 4 times x minus 2. Okay, so we just need to simplify this a little bit. Distributing out the negative 11 over 4 times the x minus 2 will get me plus 22 over 4. And then I'm just going to add the 5 over 2 to the other side, except I'm going to turn it into a common denominator of 4. So I'm adding 10 over 4. So final answer for my equation of the tangent line. It's going to be 32 over 4, but then I got to reduce. Negative 11 over 4x plus 16. Oh, no, that's just 8. Huh? There we go. So equation of the tangent line. See, a little bit longer of a process just because the derivative was more work to find, but then the rest of it was the same. Once we have the slope and the point, we just plug it back in. Okay, so we also want to be able to find, now that we know the quotient rule and the product rule, more special derivatives. So the special ones we've seen so far is sine x, cosine x, and e to the x. So we're going to add on tangent of x today. So the way we're going to find the derivative here, because tangent x we can actually rewrite as sine over cosine, which means since we have a fraction, we can use the quotient rule for this. So the derivative of sine is just cosine, and the derivative of cosine is negative sine. Okay, so using our quotient rule, low d high, low is cosine, d high would be cosine again, minus high d low, all over low squared. Okay, so simplifying this out, we're going to end up with cosine squared plus sine squared. Okay, just wanted to make sure you guys recognize, when I have like cosine x, squaring it like this is the same as writing it with a square before the x. In case you've never seen this before, but this is how it works. We usually write it with a square in front of the x, but it means the same thing as just taking cosine x and squaring it. Okay, but anyways, I'm going to have you think back to your trig identities really quick. Do you remember this one? I know it's been a while, but there was a trig identity that was like sine squared plus cosine squared equals 1. Okay, if you recognize it, cool. If you don't, this is a thing. Okay, but on top, do you see how you have cosine squared plus sine squared? This just equals 1. And on the bottom, we have cosine squared. Okay, well, 1 over cosine is just secant. So this ends up just being secant squared, or if you want to write it as secant squared, like this. So that means the derivative of tangent is just secant squared. Which means we can also use the same method to find the derivative of cotangent x, because cotangent is just cosine over sine. So we would use the quotient rule again, and then you would end up with negative cosecant squared x. Cool. With secant of x, we can also use the same method, because secant is just 1 over cosine of x. And so using the quotient rule, the derivative is 0, because the derivative of a constant, of just a number 1, is just 0. The derivative of cosine is negative sine x. So if we were to do the quotient rule with this one, oh my goodness, then low d high minus high d low all over low. So cosine times 0 is just 0, and then plus sine x over cosine squared x. So this is the same thing. I can rewrite this. 0 plus sine x is just sine x. I can rewrite this as sine x over cosine x times 1 over cosine x, kind of like how we were splitting up our limits before. Because sine over cosine is just tangent. 1 over cosine is just secant. So that means the derivative of secant x is tangent x times secant x. And using that same method, we can also find the derivative of cosecant x, because cosecant x is just 1 over sine x. So we can use the quotient rule again, and in the end, you would end up with negative cotangent x times cosecant x. So this means you have options here. You can memorize these special derivatives, or if you ever forget them, or you're like, oh my goodness, I don't remember if I memorized it correctly, you can always find it yourself. It'll take you a little bit longer, but it's definitely doable. So there's no excuse of getting it wrong for these ones. Either work it out and figure out what the derivative is, or just memorize the rules. And the last thing I want to talk about today is higher order derivatives. Higher order derivatives just means you're taking derivatives of derivatives. I know it sounds crazy, but it's not difficult at all. It actually gets easier the farther you go. So we've talked about how we would have the original equation of f of x. When I find a derivative, we would call it f prime of x. If I were to take the derivative of that derivative that I just found, this would be called the second derivative. So you're just taking the derivative of the derivative that you just found. We could even continue and find a third derivative. So we would label that as f with a triple prime, like 3 apostrophes, and that would just be the derivative of the second derivative. So let's do a quick example. If we had the original function f of x of 5x cubed minus 8x squared plus 4x minus 6, then the first derivative, f prime, would just be 15x squared minus 16x plus 4. If I were to find the second derivative, I'd just be taking the derivative of what I just found. So the 15x squared, the derivative would be 30x, and then minus 16x, the derivative is just minus 16, the plus 4 is a constant. The third derivative would just be the derivative of what I just found. So that would just be 30, because the 30x minus 16, 30x just becomes 30. The minus 16 is a constant, so that would be 0. And then if I wanted to keep going even further, after the third apostrophe, we stop writing apostrophes because, we're lazy. So we end up just like f with a little 4 on top, and that'll stand for the fourth derivative. But the derivative of 30 is just 0. because it's just a constant. And then from here on, the fifth derivative would also be 0 because the derivative of 0 is still 0. And onwards. Okay, but that's it for this section. Thanks for watching. Bye.